Hello. Can you hear me and see the
Yep.
desktop? Is there okay. Okay, everybody's here. Okay, let's see. Okay. Now, remember there's another homework assignment, but actually there isn't another homework assignment. Okay, it isn't up there quite yet. What we're because we haven't really got to where we haven't talked enough about language 3 for me to give you the homework assignment. So maybe it'll be up there this evening, but we need to talk a little bit more about languages 1, 2, and 3. And your homework assignment is you're going to do an extension of language 3. Okay, so until we really start talking about language 3, there's not much point in me putting the homework assignment up there. You won't be able to start it. Okay, so so I want to get caught up with this language 3, and then I'll put the homework assignment up there. So I think I'll put it up there this evening. So and to let you look, yeah, I mean you can start looking at it, but you may not, you may or may not feel comfortable with it yet. So we'll see how much we cover talking today about language 3. Okay, and we haven't even talked very much about language 2 yet. We've covered language 1. We need to say a little bit more about language 2, and then talk about language 3. Language 3, there's each one of these languages adds one. Our goal is to keep adding a feature to grow a language feature by feature. Remember, we looked at a list of the languages. Uh, I put it up on the website, but I didn't create a link to it yet. I forgot to put a link to this list of our languages. You remember, language 0 is our tree language. That's going to be the basis for all our other languages. Language 1 just evaluates integer expressions, 3 plus 3, 2 times 2. Okay. Language 2 adds and or and not Boolean operators to our language, and also adds a Boolean data type. So the big change from language 1 to language 2 is we go from a language of one data type, integers, to two data types, integers and Booleans. Okay. Then language 3, which your homework assignment is going to be based on, adds variables. So you could let x be 4 and let y be 3, and then you can add x and y. Okay. So this is the this is the language you want to spend the most time reading the code of, because this is the starting point, and then you add a feature to it, which is the Boolean value. Then you add a feature to it, which is the variables. Okay, here's what your homework assignment is. I call it language 3A. You're going to add two operators to language 3. And that's actually the whole assignment is for you to add two operators, the increment and decrement operators, to language 3. That'll be your homework assignment. Then in language 4, we'll add local variables. Besides having global variables, we'll have local variables. Okay, so we'll see. We're going to grow the language one feature at a time. Okay, this is the base language. Okay, that's the base language. Then these things just keep adding to it. Okay, so today what we're going to do is, well, I'm going to download these languages. Okay, the textbook for the class is reading the code to these languages. But I've tried to make the code readable, very readable. So that is the textbook. Now, but let me show you something else though. There is a textbook for this class, and I think now is a good time for me to point out to you the connection between what we're doing and that book. Okay, so I've extracted all these languages. Okay, in the syllabus, there's a link to this book, Crafting Interpreters. It's a very nice book. And it's an online book. There is no print version of it. Okay. Start reading. Okay, here's the table of contents. This book is very similar to what we're doing. The difference between this book and what we're doing, there's two main differences. We have this list of languages. The book is about this language here. What I'm calling language 7 infix is what that book is about. Instead of building from language 0 through a sequence of languages, he just describes this language here. Okay. So essentially, he just jumps. He describes that one language. Now in the book, he calls it locks. He calls the language the locks language. That's his baby language that he's building an interpreter for. I called it much more creatively language 7. And language 7 follows from, well, we're going to do language 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Language 7, but see, we're doing them as tree languages. His locks language is not a tree language. It's a traditional language like Java, C, C++, Python. It uses regular notation. It doesn't use this tree notation. We're using a tree notation like languages like Lisp, Clojure, Scheme, and Racket. It kind of makes things a little bit easier to some extent. So the two big differences between this book and what we're doing is that we're doing it as a sequence of languages, and also we're doing it as a sequence of tree languages, whereas he jumps straight into an infix language, and he's really, the whole point of his book is to build this language 7, which is essentially, it's our language 7. But here, our language 7 will be a tree language. His language 7 is an infix language. Now, I don't know if he even goes past what our, let me see. Yeah, what he does in his book, though, is after he gets the language 7, he doesn't do language 8 and 9. He does a baby compiler. He writes a compiler for that language. And in his book, we won't get that far. That's the second part of that's this part of the book. So after he builds this language as an interpreter, then he builds a compiler for that language. And we won't get that far. I really don't think we'll get to that point. Okay. So this is one language. It's not a sequence of languages. It's one language, but essentially the way he's doing it is very much the way we're doing things here. Here we're going to build the language up step by step. He kind of just describes the language all at once. Okay. Now, the steps to writing interpreters, you need a scanner. Okay. Now, see this chapter here on scanning? That's very relevant to what we're doing. And I think I'm going to make a reading assignment. You should read this chapter. Okay. See, he talks about the interpreter framework. The interpreter framework is a class called locks. If you open language 1 and you go to this file here called language1.java, that's my equivalent to his locks. Our language is called language 1. And if you open this file here, it's written like this. See, there's the main method. There's the main method. See if I can get them. If arglinks greater than 1, print a usage message. If arglinks greater than 1, there's the usage message. If arglinks equals 1, run that file. See, run file, else run prompt. Run prompt. Okay, so I'm using the same framework as he is. Okay, so this file here, language 1, is the language. It's the interpreter for the programming language, and that's his locks file. And then this file eventually does, then you have to have run file, run prompt. Here is run file. And this thing then starts using all the other files that are in the folder, the parser, the evaluator, the pretty printer. And then over here, if you go through this page, as you scroll down, he talks about tokenizing. That is talking about, in our folder, this code here, the tokenizer. Okay, and the tokenizer here is pretty close to the one he's using. Actually, I copied this tokenizer from his book, from his website. So the tokenizer I'm using here is pretty much his tokenizer. So there's an explanation of it. Okay, and then after you're talking about the tokenizer, just kind of scrolling down. Oh, okay, yeah, I'm sorry. This whole page describes the tokenizer. This is this first chapter here. Okay, so this describes the tokenizer. Then this second chapter here starts talking about the trees. This is where he talks about trees. See, we spent a lot of time talking about the tree data structure and how this thing builds the trees. That's what he talks about in this representing code. We represent code as trees. See, there's the trees. The subtraction, see, this is the tree for the expression 1 plus 2 times 3 minus 4. Okay, so he's talking about this idea of grammars and trees for representing code. Okay, so this is his explanation of what we did for trees. Okay, so read, see, there's an example. Yeah, he talks a little, he reviews the idea of grammars and languages. Here's a grammar for his language. Now, our grammar is this. We're using a much simpler grammar. So there's our grammar. Here is his grammar. Here it is. Okay. Well, it's actually, that's part of it. So there's part of his grammar. Okay. But we actually have a simpler grammar because we're using prefix tree notation. He's actually using infix notation like you use in a regular math class. See, like this. See, his language will be written that way. Our language is going to be written using the prefix notation. Our language looks like this. His language looks like that, like you're used to. Yeah. So his language looks like this, which is like a traditional programming language. Ours look like Lisp, looks like this. So that's, that's one of the big differences. We're going to work with tree languages. He works with the more complex infix language. Then he talked about implementing the syntax tree. That's the parser. That's our build tree. That's our program parse tree. So he starts talking about implementing syntax trees. Okay. And now this is where his is different than ours, because he's actually has to build, he has to write a much more complicated parser because he's working with the infix notation, not the tree notation. He has to work on a harder parser. Okay, so working with trees, okay. He has to use something called the visitor pattern to make, because it's a little bit more what he's doing is a little bit more complicated than what we're doing. And then see, he gets to hear about pretty printers. Okay, so you have to write a pretty printer. The pretty printer is the thing that takes the tree and prints it out nicely on a string. See, notice that his pretty printer produces our notation. Okay, so the pretty printer will take that tree and produce our notation. Okay, so he has a pretty printer in his language also. Okay, all right, so that's his second chapter. So if you look at his book, the first 2 chapters would be very good for you to read. Okay. Well, there's actually an introductory section. You might want to, that section 1 of the book is an introductory section. The map of the territory. He describes the LOX language. If you want, you can read that. But from our point of view, that's chapter on scanning, and this chapter on representing code is very much like what we're doing. Here's where he really goes into his parser in detail. We don't have to do that. Because we're using a tree language, we don't need a real parser. We can do this build tree, which is a very simple. Our parser is just going to be, our parser is just 60 lines of code, 50 or, and remember, most of this parser is doing error checking. Okay, so our parser altogether is 80 lines of code. Very simple parser because we're doing a tree language. His parser is a lot more than 60 lines of code because he's doing a real recursive descent parser. We'll talk about this when we get to the end, when we want to put an infix notation on language 7. Towards the end of the semester, we'll come back and we'll write a real parser for our language 7. And then that's when we'll be kind of doing what's in this chapter of the book. Okay, so this is a real parser. It's a pretty long chapter because that's not a trivial matter. Okay, and then this chapter 7 is back to what we're going to do. That's what we're really talking about now, evaluating expressions. That is our evaluate file here. This evaluate file here is his chapter 7. He describes that. Okay. Later on, when we get to language See, like when we get here to language 6, we'll add loops and conditionals. We'll see in his point of view, that's this chapter like 9. See, he tells you how loops and conditionals work in chapter 9. Okay, so, and then he does functions in chapter 10. And in our case, functions will come in language 7. By the time we get to language 7, we'll be kind of caught up with this book. Now, he's actually talking about only one language. The difference is he's presenting the material in the same order as we are. First you parse, then you evaluate, then you do if statements and you do if statements and loops, and then you do functions. But he's talking about the same language all along. In our case, we will grow a language. We'll grow a language that adds those features to the language. I think this is kind of an interesting way to do it. Instead of having one big language and then just studying pieces of it, I think it's kind of nice to have a language that just does this, and then you could see how you add to that language to do this, and then how you add to the language to do this. So when you want to do conditionals, you just have to, you add that to the language. In his case, everything's in the language to begin with. If you look at his code, the code is the LOX language. Now his code is up on GitHub. So the actual code, see if I can find the link to it. If I remember, trying to remember where he has the link. The code is up on GitHub. It's kind of weird. He buries the link to the code. You'd think it'd make it really obvious. Now remember that the link to the code is buried somewhere in here. And I can't remember now where it is. And you think it's like a little weird mistake because you think he'd make the code itself real prominent. And now I'm forgetting where he buried the link to the code. It was near the beginning. Maybe it's here. But it's weird that you'd think that there would be a big link saying, here's where the code is, unless I'm missing it. I remember struggling to find the link to the code another time. It's a very nicely done book. It's very well written. It's got nice pictures. It's got nice ideas. It is very good.
He's
And
humorous too.
Pardon me?
He's humorous too.
Oh yeah. He's a clever writer. He works for Google. He's one of the designers of the Dart language. There's a language that Google designed several languages. Go has been really successful, but they also designed a language called Dart, which wasn't. It still exists, but it's not as popular as Go has become. But he's one of the designers of the Dart language. That's one of his claims to fame, is that he's on the Google team that's designing Dart. Oh, I wish I could find it. Yeah, somewhere. Probably if I Google it. Yeah, this is it. So Google, maybe, maybe he's just assuming that you're smart enough to do Google instead of looking for links. Okay, so here's his GitHub site, and then this is the repository for the LOX language. Okay, and this let's see, this is the code for the book. So these are the markdown files that are the book itself. The interpreter code here. Okay, So there's the interpreter code for locks. There's the parser. There's the file that starts everything I showed you a minute ago. There's the file that's like our language one. So language1.java is equivalent to this guy's locks.java. Interpreter.java, I think, is the equivalent of this evaluate. Okay. The scanner is what I call the tokenizer. It's because half the world calls them tokenizers and half the world calls them scanners. Token represents one token. Okay. I didn't use his token type. He's got token and token type. I wrote a version of this using token type, and I thought, it's overkill. So if you read about his version of the tokenizer, he has something called, he has a token and a token type class, and I decided not to use the token type class. It is in a real programming language, tokens have a token type, and maybe later on we can add it back in and see what good it does us. But I thought it was a little bit overkill for a simple thing like this. So scanner is the tokenizer, token is token class. Not sure which one of them is his tree class. Maybe, I don't know if it's expression is his tree, because he does trees a little bit differently. That's one of the things he does. He does the tree data structure. Since we're a tree language, I kept the tree data structure real simple. He's not doing tree languages. He's doing an infix language. I think this expression class here is the equivalent of his tree. See this file here, environment? We'll need it in language 3, because environment's where variables get stored. So language 3 has environment. Language 1 and 2 don't have environment, because environments are where you store variable. Environments are essentially like stack frames. We'll see that environment is where you keep track of what's the value of X, what's the value of Y. Okay, that's called the environment. So we don't need an environment until we get to language 3. Language 1 and 2 don't have variables, so there's no need for an environment. So there's his whole language and there's our language. Okay. And this one is kind of very loose. Actually, I wrote this before he wrote this book. I wrote this years ago. And I was kind of surprised when I saw his book, how closely they matched up. So it's just that there's really only one right way to design an interpreter. And so the way I wrote it and the way he wrote it is the right way to design an interpreter. So it's not such an odd thing that they would look very similar. I did steal his tokenizer from him, and I did model this file here, language1.java, off of his locks.java. So the two things I took from him that I thought were really good ideas is the way he wrote this file and the way he wrote his tokenizer. I thought those were very nicely done. So I copied his tokenizer and the file. Now, what this file does, now I've taken this file and I did something he didn't do. I compiled everything into a jar file and then wrote a little batch file that runs that jar file. And there's our language running as an interpreter. We are doing here we're running if you open this file here, we're doing the run prompt version. See, we're running a prompt for the language. So I have a prompt for the language where I can do things like +3, 4. Okay. So I've got this language giving you a prompt, and that's what, this came from. I got the idea of this from his locks language. He writes a locks prompt that lets you, just like notice that this is just like the JavaScript shell or the Python shell. It lets you execute statements in your language at a prompt. Okay. So I can do the multiplication of the sum of 4 and 5 with 6. So I can evaluate expressions. Okay. Now, one thing my language does that his doesn't do is every time you type in an expression, it builds the tree and shows you a picture of it. See, +3, 4 was that tree. Times 4, 5, 6 was this tree. So I had the idea that as you type expression, it'd be nice if the language would use GraphViz to draw you the tree. In his book, he shows you these trees in pictures. What happened to the? Yeah, see, here's how he draws pictures of these trees. Well, why not have a program draw pictures of the trees for us? Okay, so for example, in my interpreter, let me type a kind of complicated expression. The sum of the product of 8 with the subtraction of 6 and 2. And then I'm going to add to that, say, 100. And then I'll also add in, say, the product of, say, 6 and 7. Okay, so I'm summing 3 things. The product of 8 with the subtraction of 6 and 2, 100. Okay, so hit enter. Now, that kind of complicated expression, see, there's the tree for it. It was a sum of 3 things. It was a sum of the product of 8 with the subtraction of 6 and 2, the 100, and the product of 6 and 7. Okay, so I thought it was really nice to see. That's a little, we call that instrument. I instrumented the interpreter to provide a picture of the tree data structure that it built. Essentially, this is like a debugging thing. So the interpreter is instrumented to, every time you type in an expression, it gives you a picture of the expression. Okay, so I think that's actually very nice to be able to see the pictures. Python could do this too, and there actually are versions of Python, if you know where to look, where as you type in Python commands, it'll draw the abstract syntax tree of the Python commands. You know, this is not a unique idea. And it's used by people sometimes for debugging purposes. Usually it's if you're debugging the interpreter itself. Usually you want these trees if you have to debug the interpreter, or you can use them to learn about the interpreter. Okay, so this is something our interpreter does that his book doesn't do. He draws these pictures, but he just drew these himself. Instead, I'm doing it automatically. Our code, the code in this here, if you go here, when you call run prompt, it goes down here. This is the run prompt. It reads what it uses scanner to read a line that you typed in, and then it tokenizes it and parses it. And then here's where it builds the app. Here's where it tells GraphViz to draw a picture for you. So this code here is the code that says to GraphViz, draw me a picture of the tree that I built. Okay, so here's where, so you read the line of code that the person types in, build the parse tree for it. After you build the parse tree, ask GraphViz to draw a picture of it, and then evaluate that tree. See, here's the actual interpreter right there. After I have GraphViz, I draw the picture here before evaluating it, so that if this thing's got a grammar error in it, I want to draw the tree that's like, suppose something, here's what I mean. Suppose I type in something like this, times 4 with the product of 3 with, okay. Now, I've got an error. You can't take the product of one number. So, oh, let's see. That shouldn't have given me an answer. I wonder why they, oh, I have to go look. Oh, I probably forgot to add, I think I forgot to add one of the, remember we were looking at, remember how the other day we added more error checking to the evaluator? I think I forgot to add one more error checking. I think I'm still missing a couple of error checks in the evaluator. It should, a product of one thing shouldn't mean anything. Now, remember we did this one? See? The division of one thing doesn't mean anything, so we catch that as an error. And we added this one. If you take the division of 3 things, we added so I forgot to go and fix the product one. I should get an eval exception here. Okay, So suppose I do something like the product of 6 with the division of 4. Now that's the error. Okay, so that didn't work, but I still get a tree for it. I still get a tree because the tree is built before I try to evaluate it. So there's the invalid piece of the tree. See, that branch there, the parser built it, but the evaluator doesn't like it. So the parser built that tree, but then the evaluator said, I don't like that branch. Okay, so just in case the evaluator blows up or does something weird, I went ahead and had the tree drawn before calling the evaluator, just in case the evaluator's got a bug in it and it crashes. That way, it helps me see what was wrong with the expression before the evaluator. If the evaluator crashes on me, I could at least see what it was trying to evaluate, because I get one of these pictures. I get a picture here of what the evaluator was trying to evaluate. So, for example, this one that I have to fix, okay, that doesn't make sense. But I can see here that it was evaluating that tree. So the tree was the product of 4 with nothing, and the evaluator's got a mistake in it. It should catch that as an illegitimate expression. That should give us an eval exception. Okay, and it's actually, we can look the code. I know exactly where the mistake is going to be. It's just like we did the other day. The other day we added these checks here. Remember, they weren't there and we added them. Well, we need a check just like that now under the product. Okay, product needs a tree that's at least 2 branches big. Okay, so here I need, oh, hit the wrong key. Here I need, if degree tree is less than 2, okay, so if the tree degree, yeah, star should have at least 2 operands. Okay, so I can fix it. Now, remember how I fix it? I've added a bug fix to evaluate. In our system, I go now to here, click clean to delete all the class files and everything else. Build all the classes. Okay. Build a jar file. Okay. Now I have a repaired language. Okay. Okay. See, notice how easy it is. There's lots of little details I still have. I'm finding time to. You don't find these errors unless, like I said the other day, you find errors by using the language. That's why you need unit tests. I really should have I should have a folder here of unit tests that just pump expression after, like, hundreds of expressions into the interpreter to make sure the interpreter is covering everything it should. But I haven't had time to do that. So there are going to be every once in a while we'll catch a little bug in the interpreter because I haven't tried enough expressions yet. So like now we realize that, oh, there should be something that catches the fact that product has, the multiplication operator needs at least 2 operands. So the multiplication operator needs at least 2 operands to be correct. Okay, so as we go along, we'll if we catch little errors in the language, we'll fix them. So we just fixed that one there. Okay. All right, so this is our language system. Like I said, it's pretty close to his language system. His language system, the parts that you can get the most out of for now is his chapter 4, chapter 5, and chapter 7. So I'll create a link. I'll put it up on the course website that you might want to read for, because we're using his scanner. The representing code is really just basic theory. All interpreters represent code as abstract syntax trees. Everybody does that. All interpreters, all compilers, they all use the same idea that you take the code and you parse it into an abstract syntax tree. He uses a more complicated parser than we did, so we can skip chapter 6 because we don't need a fancy parser right now, and then go to chapter 7, which is on evaluating basic expressions. Like in our case, we're evaluating arithmetic expressions. And that's pretty much, I think, what chapter 7 covers. I think chapter 7 only covers arithmetic expressions. Okay, so, all right. Now, let me close some things here. Okay, now, language 1, like I say, it only does arithmetic expressions. Well, actually, so here's the language that is language 1. Okay, now language 2 adds a little bit. Okay, see, language 1, an expression is an arithmetic expression or an integer. In language 2, an expression is a Boolean expression or an arithmetic expression or a Boolean literal or an integer literal. Now, a Boolean literal is only the keyword true or the keyword false. The integer literals are, that's the way, an integer literal is an optional minus sign. Oh, and actually this should be a plus or minus sign. You could put either a plus or a minus sign in front of an integer. I forgot, I should have, the minus sign is useful, the plus sign's not useful, but it's allowed in the language. Almost every programming language lets you write in it, you're always allowed to write things like +5, minus +6. That's just another way of saying 5 minus 6. Okay, so you can write a plus sign in front of your integers. Okay, so that's perfectly, so I actually should remember to change that. You can have a plus or a minus sign in front of your sequence of digits. Now, these are integers, they're not decimal numbers, so there's no decimal point or anything like that. Okay, so a plus or a minus sign in front of a sequence of digits. Okay, so that's, so an expression is either a Boolean expression, arithmetic expression, a Boolean literal, or an integer literal. Now, the arithmetic expression here is exactly the same as it was in language 1. That hasn't changed. Oops. So here's arithmetic expressions in language 1. That's the exact same thing in language 2. Okay. Assuming I meant them to be exactly the same. I hope I didn't make it goof up, and think I got them exactly the same. Okay. Because we're supposed to, the idea is that every language, the grammar will include the grammar of the previous language. So languages 2 grammar should include languages 1 as a sublanguage, and languages 3 grammar should include language 2 as a subgrammar. Okay. Here's the new stuff. What's a Boolean expression? A Boolean expression is oring, anding, not. Notice not's a single operand. Oring is like adding and multiplying. It can have, well, it's actually like multiplying. It needs 2 or more operands. It doesn't make sense to say and x. Okay, you need to and at least 2 things. Same with or. So or and need 2 or more operands. So they're like multiplication, 2 or more parameters. Okay, not is unary, so it takes 1 parameter. And then there are the relational operators. The relational operators are less than, greater than, less than or equal to, and greater than equal to. And there's the equality operators. Okay, the equality operators are equal or not equal. Okay, so the Boolean expressions are the regular Boolean operators and or not. And then relational operators, now these will be arithmetic expressions. It doesn't say that here, but these actually should be arithmetic expressions, because this asks for the only thing you can compare are numbers. So this would be the relational operation. These should be integer expressions. The equality operator works on either Boolean or so you could ask is true equal to false, or you could ask is 4 equal to 5. Okay? Or you could ask is 4 equal to true. If you ask if 4 is equal to true, you'll get it's just false. The relational operator will crash if you ask it something dumb. If you ask is 5 less than false, that's an error. You're not supposed to do a relational operator between mismatching types. So we'll see that that would be an error. You shouldn't ask if 5 is less than false. In the C programming language, you can. In the C programming language, what is 5 less than false give you? Does anybody know how C does that? What's the meaning of false in the C language or in C++?
Maybe false can be represented with 0.
Yes, it is represented by 0. It is.
Okay.
It is 0. So
Okay.
is 5 less than 0?
No, false.
No. So this thing returns false.
Mhm.
On the other hand, if you said is 5 greater than 0, it'll be true because false is 0. Okay. So you can also ask is true greater than false? In C, what's the answer to that?
True.
Because true is what?
1.
1. True is the number 1. Okay. And
Mhm.
false is the number 0. So you can compare true and false. No, now Java won't let you do that. If you type this in Java, you'll get an error message. You cannot compare Booleans, and you can't compare a number to a Boolean, okay? Because they're considered different data types. They don't have a comparison. Now you can ask that, and that's just going to be false. 5 is not equal to false. That would be legitimate in Java, and it'll just return false. That will be false. Let's see. No, let's see. Suppose you did that. In C, true is 1, so 1 equals 1. In Java, this is a different data type than this. And whenever you compare values of different data types, they're never equal. So you get false because it's never the case that 2 different data types are equal to each other. That's an integer data type, that's a Boolean data type, so they can't be equal. So in C, since true is 1, that would give you true. 1 equals true. Okay. In our language, if we go here to language 2, we can run the interpreter by going here and double clicking this. And I can do, okay, equal 4 with the sum of 2 and 2. Okay. The value is true. Okay. 4 is equal to 2 plus 2. Well, what about is true equal to 0? See? Error. You can't compare, not an integer expression, true. Equal expects to compare. Well, actually, I wrote it so the equal only works on integers. So I actually wrote this language, and maybe I should change that. If you try to do this, see, it gives you an error. The way I wrote it, equal only works on integers. So I probably should change that. It's legitimate to ask, is true equal to false? And the answer should be that they're false. So it should be legitimate for me to say, is true equal to greater than 5, 2. Okay. True is true. Greater than 5, 2 is true. So this and this give you the same result. And so this thing should be true, but it gives you an error message. I think I'll change that. I think I'll change the language so that equal works on both Boolean data types and integer data types. But right now it's written so that equal only works on integer data types. Some languages work that way. Some languages, the equality data types only work on, the equality operators only work on integers. Okay. All right. The relational operators should only work on integers. Those should only work on integers. But it is reasonable for these to work on both Booleans and integers. But I have to make an adjustment to the interpreter to change that. Okay. All right. So this is the grammar we're working with. Now everything's written as a tree language. Okay. So everything is written the way I did it over here, using Lisp, scheme, closure-like notation. You don't write okay. We'll be able to, that just doesn't parse because that's not a tree. Okay. Later on, when we get to towards the end of the semester, when we get to, oh, where am I? When we get to giving language 7 an infix notation, that's when our language will accept things like 2 + 2 = 4. See, that's the infix, the traditional notation. But that's the notation that's much harder to parse. So we're kind of avoiding that. So we don't have to spend a lot of time talking about how you parse express. It takes quite a bit of work to parse things like that. That's not a trivial matter. So we're kind of avoiding that by using this tree notation, which has got a long tradition in programming languages. A lot of programming languages use this tree notation. Like I say, Lisp, Clojure, Scheme, Racket. There's a whole bunch of languages that use this tree notation. And it's nice because the tree notation's super easy to parse. Okay. Now, notice that this thing's returning weird things here. Like if I do plus of 4 and 5, I get back this funny thing. Here's the idea. The interpreter doesn't know what I'm about to do. So sometimes I give it an arithmetic expression, and sometimes I give it a Boolean expression. So sometimes the value it gets are arithmetic ones, and sometimes the values it gets are Boolean ones. Notice that here, this is, see, 4 + 5 gave us a value with a tag of int. The tag int means that we read the int value and we don't look at the Boolean value. Here, this thing gave us a value with a tag of Boolean, which means we ignore the int value and look at the Boolean value. This is how all modern dynamic languages work. Languages like Python and JavaScript, since any variable can hold any data type, the variables actually hold multiple values in them. So a value, essentially every value is simultaneously an int and a Boolean. And then there's these are called tagged unions. There's a tag inside the value that says which of these two is the one you should look at. So if I'm returning an integer value, I stick the integer value in that field and set the tag to int. If I'm returning a Boolean value, I stick the Boolean value in this field and set the tag to bool. Now, if we look at the source code, let me clean this up so we can look real. See, there's a class called value. This class represents the return value from evaluating an expression. A value object holds 3 fields. It holds a tag field, which is a string, which is either going to be int or bool. Then it holds 2 other fields, an int field and a Boolean field. We use this value to represent either ints or Booleans. But so you could put a number in here and you could put a value in here, but then the tag tells you which one of them to look at. This is how modern languages allow you to, like in Python, in Python, you're allowed to do the following. In Python, you could let X equal 5. Then later on, you can say let x equal hello. Then later on, you can say let x equal 6.43. Then later on, you can say let x equal the list A, B, C. Here, x has type int. Then all of a sudden, it changes to type string. Then it changes to type double. Then it changes to type list. And since Python doesn't make you declare variables, this is allowed in Python. What that means is that the Python values are stored in a thing like this. And the value simultaneously carries around. In the case of Python, it would simultaneously carry around an int, a double, a string, and a list possibility. And any given value, the tag tells you which one of these fields holds the real value. And that way you can have a single variable that can switch between, sometimes it's holding an int, sometimes it's holding a string, then it's holding a double, then it's holding a list. Now, Java won't let you do anything like this, because in Java, you have to say int x or double x. Okay, once you say double x, you can only put double values into x. X can't hold anything but a double. But for example, in JavaScript, you would say things like var x. That means you have a variable x, but it doesn't say what it holds, because it can hold anything you want. So in JavaScript, you could say var x, then later on make it an int, then later on make it a string, then later on make it a double, and then later on make it a, okay? Because what JavaScript does is it has a value type like this that has a tag in it, and the tag says what it's really holding, and then depending on how it's set up, it could actually literally have a field for every possible type of value. And there will be a list of tags that are allowed, all the different tags that like all the different types that the language might offer, like int, string, double, list. Okay, so we have this value class that represents the value of expressions. If we think of it in terms of the grammar, see, expression is of type value. See, expression is of type value. All of these are of type value, but a Boolean expression will return a value with the tag set to Boolean. And an arithmetic expression will return a value object with the tag set to int. Okay, so all expressions have type value. And if we look at the evaluate code, here's the evaluate code. See, eval returns a value object. But so that value object can represent either int or bool. Okay, depending on what tree you evaluated, if it was a tree representing a Boolean expression, this value will have the tag Boolean. If this tree represented an arithmetic expression, this tag will have the value int. But it doesn't matter if this tree is, see, you get the same kind of value back. It doesn't matter whether you evaluate a Boolean expression or arithmetic expression, you get back a value object. Okay, and then the value object tags itself to say, oh, by the way, I'm really a Boolean value, or I'm really an integer value. Okay, and the way I did here to keep things simple, I actually, the value class actually literally has in it an int value and a Boolean value. And you actually, depending on the tag, you look at one of them and ignore the other. Depending on what the tag is, you look at this one or you look at this one and you ignore the other one. Okay. All right. So, and as this language grows, we're like, we'll add more tags and more fields to values. So if we wanted to give this language doubles, we would create a third tag. Here's the, we would create a third tag and put a third field in here. There was a double field. And then we could have expressions that returned doubles instead of just integers. Okay. And then we'd have to grow our language to have expressions that return double, which gets to be kind of complicated because these guys return integers, and it's actually a little bit tricky to give this language doubles, because unless you want to give different operator names, like you could have an integer addition and double addition. And there are actually other languages out there in the real world where there's one symbol for integer addition and a different symbol for decimal addition. And some languages are very picky about this stuff. You don't add an integer to a decimal because they're different data types. Okay, we're not going to go that far. In fact, we're going to avoid the decimal data type for this reason. So we're going to kind of avoid the decimal data type, because otherwise you have to overload these operators and it gets kind of tricky. You have to overload the operator, and what this thing has to do is have to say, if this guy's an int and this guy's an int, I return an int. If this guy's a double and this guy's a double, I return a double. If this guy's an int and this guy's a double, what should I return? If you're doing addition and he's an int and he's a double, what should you do?
It should be double.
You should do what? Convert the
integers to double.
And then add them, which is what the compiler in Java will do. If you add int to double, the int gets converted to a double and then gets added to the double to return double. But that's a lot of, that would be a lot of code in our interpreter, but we could do that, okay? So then you have to overload the plus symbol to handle all these cases. Int plus int plus double, double plus int, double plus double. Okay, and you'd have to have, and that just adds a lot of code to the interpreter. Okay, and that's how Java does it. Java overloads the plus. There are languages out there that you are not allowed to do. Haskell is an example of a language like that. That's an int, that's a double, and you can't add them. You'll get an error message in Haskell. You have to do something you have to call a function that converts into double, and then you can add the result to the double. So you have to call a little conversion function here that converts the int to the double. Essentially, you have to cast yourself. You have to cast the int to a double yourself, because it will not automatically convert an int to a double for you. So there are languages that say you should never add an int to a double, that something's wrong there. Most languages will let you do it, but some won't, okay? Right. So in our language, this guy represents all possible values, which in our case so far means it represents both the integer values and the Boolean values. The evaluate function, if we go down here, the eval function, okay, the eval function returns a value object. Now, if you look what happens if you get down here. Look for, here's evaluating an ampersand. So that's evaluating a Boolean operator, okay? Let's see. Here's where it sets, see, here's where it creates, well, it calls eval on this, oh, I'm sorry. Suppose you're, okay. Ampersand has to have a left branch and a right branch. So first evaluate the left branch. Check that its tag is a Boolean. Why do I do that? I'm doing an AND operation. I'm going to iterate through all the branches of its tree. So I look at the first tree, I evaluate that left branch, then I check, is the tag bool? Why do I want to do that?
You want to know if they're ANDed or not.
Pardon me?
You want to know if they're the same or not.
What's the same?
The value of the Boolean, true or false.
Well, okay, what am I looking for? See, what if somebody wrote a program that looked like this? What if somebody said, take the AND of true with the addition of 4 and 5. That's going to give me a tree that's an and with a right branch and a left branch. On the left branch, there's the keyword true. On the right branch, there's a sum of 4 and 5. Okay, so the interpreter checks the left branch, gets a Boolean value. Then the interpreter checks the right branch. What does it get back from the right branch?
An integer value.
An integer value.
Arithmetic.
Right. So then it says, but I'm doing and I get something that's not a Boolean. So what should I do?
Throw an error.
Throw an error. See? Throw an error. Because this shouldn't work. The truing of you should and two Boolean values. Okay, so when the interpreter says this is 9 and it returns 9 to here, this branch is 9, then the and sees Boolean on the left, integer on the right, throws an error. See, so that's what now if this was a compiled language, what would happen?
I want to say compile error, but
Why not?
compilation.
Because the
But maybe-
compiler says that guy is Boolean, that guy's integer. So the compiler just stops and says, I refuse to compile this. Because what?
Data types don't match.
Data types don't match. You get a type error message. Yeah, so the compiler refuses. Now, in Python, what happens? Well, this is okay. You can write that in Python. When do
Runtime.
you find out that this was wrong?
In the middle of your program running.
Exactly. And if this is the code that's landing your airplane, that's a bad time to find out that there's a type error, which is not a trivial matter. This is why nobody writes really important code in Python. You understand? This is important. That's why languages like Python and JavaScript are not suitable for really important programs. You do not write code for airplanes in JavaScript and Python, because otherwise, how in the world would you know if there's a type error in the middle of a 1,000,000-line program? The code that lands an airplane is 1,000,000 lines long. How do you know that there's, the fact that a compiler checks everything before you run the program is incredibly important. You don't want to find out at see here, you don't want this to be shown up at runtime, which is exactly what we're doing. This is how Python works. This is how JavaScript works. It isn't until you run the program that you find out. Because here's the trouble. This is obvious, but now watch this. Is there a type error there?
You don't know unless you know what those variables represent.
Exactly. And at now the compiler, what does it know?
What the variables represent.
Right. So it can tell you at compile time there's a type error. But the interpreter, see, here's the problem with an interpreted language. Watch this. Here, this is completely valid JavaScript. Okay, why am I showing you here? What's this demonstrating? Oh, oh no, I messed that up. That doesn't make sense. I need to change the expression a little bit. So, okay, what does that show you?
Ooh. Well, it kind of made sense at first, but then when you change W to 5, I don't know.
Okay, there. So this is a dynamic language. So you go
Okay.
through here. W is false. X is 3. Y is 4. What about this guy?
So false and is X less than Y? True.
Okay.
So false and true is false.
Okay. So this thing interprets correctly, right?
Mm-hmm.
Yes.
Now X is true. W is 5. The exact same code again.
Now that part doesn't make sense.
How can you now notice that? How can you tell that here it's legitimate and here it's not legitimate? Now, what if between here and here is about 2 million lines of code where, somewhere X is set to here and somewhere Y is set to here, and then you get this? How would you know that this one is legitimate and this one's illegitimate? Could you analyze the code?
I mean, you could, but it would take you forever to
How would
find
you
it.
analyze the code? You'd run the program essentially.
Yeah.
And that's actually, you can actually prove that as a theorem, that when in a language like Python, the only way to know whether there's a type error is to what?
Run your program.
Yes. There's no other way to check if there's a type error. You must run the program to find out if there's a type error. Now, on the other hand, if you have a compiled language, you know there's type errors because up here you would say bool w int x int y. Okay, with this information, you know that this is correct. With this information, this one's not allowed. See, then the compiler stops you there. You can't put a Boolean in an int, so this won't compile. This is correct because it's assuming that X never is anything but an int and Y is never anything but an int and W is never anything but a bool. So a compiled language with types declares what everything is, and you can tell at compile time whether the code is correct or not. Without this information here, without that information, you have no idea if this is correct or not. That's the situation you're in JavaScript and Python. How does the JavaScript world deal with this? Does anybody know how the JavaScript world deals with this problem? They invented a new language. Typescript. JavaScript with types. Instead of writing JavaScript, you can write TypeScript. This was invented by Microsoft, and it's being used by a lot of people now because JavaScript without types is a mess. TypeScript is JavaScript with types and a compiler. Okay, that solves a lot of the problems with JavaScript. And a lot of what are large programs in JavaScript now are actually being written in TypeScript. A lot of people are writing them in TypeScript rather than JavaScript. It's an extension of JavaScript with types. Guess what it compiles to? If you're writing TypeScript instead of JavaScript to write your web applications, what do you think the compiler would compile the TypeScript into? What runs in the browser?
Mm,
URLs? What? No.
No, what code runs in a browser? JavaScript.
oh,
Right.
So TypeScript compiles to JavaScript.
Nifty. So they
Hmm?
they iron out the issues if there's any, and then just say it's JavaScript.
Yeah, and then they strip after they figured out that there's no type errors, then they strip out the types and it's JavaScript. What they would do, what TypeScript more or less does is once it figures out that this is okay, then it just removes this from the code and then what's left is JavaScript. It's very clever. Okay. And it lets you run programs that are more or less as safe as programs like Java, because Java has a very good system of typing that makes your programs very safe. So you can add typing to JavaScript, and then once the compiler sees that all the types work out okay, then it deletes the types, and what's left is basically JavaScript, and then that's what you run in your browser. But now it's JavaScript that you're pretty sure is safe. It doesn't do anything stupid like this. Okay. In our language, when we do add it variables in language 3, okay, let me go to language 3. Here's the language 3 interpreter. I say var x. That's how I declare a variable. Okay, now I have a variable x that represents 5. And I can say var y. I'll make that 4. Okay, so now I have an x and a y. Okay, and I could add x and y. Okay, now I can do set x to be false. Oh, let's see. I think no. I just say var again. Var x false. Now, what happens if I add x and y? Now it doesn't work. See, x changed its tag from int to bool. So, x was an int for a while, then x turned into a bool for a while. This same expression, adding x to y, was valid at one point. See, it was valid at one point and then it became invalid later on because variables can change their type, just like in JavaScript and Python. In this language 3, you can change the type of a variable just by giving it a different value. So whatever value you gave it last, that's what type it has. That's exactly how JavaScript works. Whatever value you gave it last, that's what type it has. Okay, so here W is a Boolean, but all of a sudden it turns into an int. That's how Python works. That's how JavaScript works. And that's how our language 3 works. Okay, whatever is the last value you give the variable, that's what type it has. But that's not. But that means that when you do something, that means that the code for doing addition has to keep checking the types of its operands. So see, what happened here was that when I did up here, when I did plus x and y, the evaluator checked what x was and got an int, and checked what y was and got an int, and said, okay, I'm safe. I got 2 ints and it did the addition. Here, when I did it here, the evaluator checked what x was, then it checked what y was, and it saw that one of them is not an int through the eval exception. And we can go to the code for the evaluator and see that. So let's go to language 3. Go to the evaluate. Find where it's evaluating addition. So you have to kind of scroll down, look for where you have node equal to addition. I think it's farther down. Here's addition. Okay. If there's only one operand, that's you return it. Okay. Otherwise, now here's where you have to go. You step through the degrees, you step through all the branches of the tree, you evaluate a branch and then check that its tag is int. Every time you check one of the operands of addition, every time you check one of its operands, you have to say, but did I get back an int? Did I get back an int? So now that slows the program down. See, a compiler would know ahead of time that these things are all correct, but an interpreter has to keep checking. It gets the first operand. Like, for example, here, let me do something. Var x9. Okay, so now I can do plus x, y, 7, 3, x, y, x, y, y, x. Now I'm adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 operands. The evaluator had to get that x, check that it was an int. Get that y, check that it was an int. Get that constant, check that it's an int. Get that constant, check that it's an int. Get that constant value, check that it's an int. Notice that the interpreter had to check all 10 of these at runtime to make sure that they were ints. Guess what makes JavaScript slow? Guess what makes Python slow? They have to work this way. If you're going to add a bunch of things in Python, it isn't until you do this command that Python can even find out if x is an int or not, because Python has no way of knowing ahead of time what you might have stored in x. A compiler knows ahead of time what every variable represents. It doesn't know what values in the variable, but it knows what kind of value it is. So an interpreter is slow, but a compiler would be fast because compiler doesn't need to check these things. It's checked at compile time. At compile time, you know they're all ints, so you can add them all up. The interpreter has to step through the tree, evaluate one branch at a time, but then check that every branch returns an int. If any branch doesn't return an int, you throw this eval exception, which is, and that would be like here on that branch. See, on the 7th branch, it hit something that wasn't an int. Okay, so when it got to the branch that wasn't an int, then it hit this eval exception. Okay, all right. So we ran out of time. So what we'll do, let's see. So today's Wednesday. On Monday, we'll go back through and we'll systematically go through we need to systematically go through exactly all the steps of these two interpreters. Okay, so we'll go through them again. Everything in language 2 is part of language 3. Language 3 adds that thing, the thing that lets it keep track of variable. Well, it adds this thing and, no, I'm sorry. Language 1 is a subset of language 2. Language 2 adds that thing to language 1. That's the thing that lets us hold either integer or Boolean values. Then language 3 adds that thing, which is the thing that stores the variables. So language 2 adds that to language 1, then language 3 adds that to language 2. And that's pretty much the change. There's really more or less one important change per language. Okay, so a value type to keep track of the type of the values, and an environment type to store the values for all the variables. Okay, and we'll talk more about that thing there, the environment. And if you read that guy's book, he has an environment in his language too. I'm not sure where, I haven't found where in his book he introduces the environment. I should look to see where it is where he introduces the environment. Maybe, I don't know if it's in this chapter 7 on evaluating expressions. No, there's no environment mentioned in this chapter. Okay, so yeah, but the environment is the thing that language 3 adds to language 2. Okay, so that's what we'll go through real carefully. We'll try to go through that real carefully on Wednesday. Meantime, read the code of read the code for these. That is the book. Read the code, like for language 2. Start with the entry point, language 2. Look at what it calls. Go through these other files. It's not as much as you might think there. There's because a lot of these files are not very important. Eval exception is 5 lines of code. It just defines an exception type. So it's not very useful. Okay. Same with token exception. Same with parse exception. So there's 3 files there that are just 5 lines of code each. Okay. So quite a few of the code is just boilerplate, stuff that doesn't really mean much. We've covered tree, so you shouldn't have to talk about, the tree part you should know, the parse tree part you should know. So you look for the parts that are new, like what did language 2 add that language 1 didn't have? What did language 3 add that language 2 didn't have? Grow the language. That's our goal, is to understand the language by growing it. Okay, so we run out of time. Let me quit there. I don't know. I'll put homework 2 up probably this evening. You can look at it. You might know enough at this point to start on it, maybe. But if you don't worry about it. I'll set the due date that's here. I'll probably extend that. Probably won't be due the 10th. Okay. So when I get, I'll give you a little bit more time, because this assignment, there's a fair amount for you to figure out, because you have to digest the language structure. The point of the homework assignment is essentially to force you to read this so that you know enough about this code that you can add to it. Okay. So we'll go ahead and quit there. So have a nice weekend. We'll meet again on Monday. If you have questions about the current homework assignment or about this other stuff, send me an email or come to office hours tomorrow. Okay. So have a nice weekend. Bye.
Bye. Thank you.